So now we're going to look at how to implement in TensorFlow those ideas that we saw in the previous lecture. We're going to see the basic types in TensorFlow, how to chain all these basic operations, and I'm going to give you some examples that you'll follow then in the tutorial, implementing logistic regression as a simple single neuron, solving the OR problem with one neuron, and then extending that to the exclusive OR, which requires a small multi-layer perceptron, and the other data sets that we have here. That part will be for you to do on the tutorial. We're going to be looking at the very basic elements of TensorFlow, and so we're going to build very small networks just to look at how these things work. In future lectures, when we start looking at more complex architectures, we will be using the Keras interface to avoid having to write lots of code just to do anything. But this first part is important so that when you start using that more powerful interface, you understand what is happening at a lower level. So let's start with the basics. TensorFlow, as we saw, will create this computation graph. Each node is an operation, and each arc is a tensor, so an n-dimensional matrix, which flows, takes the data flowing in the graph. This is necessary because remember that when we are creating, chaining together these computations, these operations, TensorFlow needs to keep track of also of all the derivatives and know what the derivatives are. So actually these objects that we use are not just the matrix of data, but they are more complex, both the tensors and the operations, so that all of this can be done behind the scenes, and we don't have to worry explicitly then about how to compute the derivatives and so on. If you look at documentation for previous versions of TensorFlow before 2.0, you will see some examples where the computational graph is first created and then it is executed in a session. With eager execution, which is the default in the current versions of TensorFlow, this is a lot more practical, a lot more imperative, because each operation is executed as the interpreter is running your code. So this will be what we will look at now, where we are using eager execution. This is the default. Next week, we will see how to create the computation graph and then run it, because that is something you can also do if you want to optimize the execution. Because if TensorFlow has the whole computation graph, it can decide better which parts to send to the GPU and the CPU and so forth. Also, if we create a computation graph, then we can use TensorBoard to look at the graph. Those diagrams that I've been showing you with the operations are created by TensorBoard, and we will see that next week. But for now, we'll use eager execution. So if you just want to do a simple operation using tensors, you can import TensorFlow and then create, for example, these constant values, 3 and 4. You can add names to the tensors so that when you look at the computation graph, you see the tensors with their names there. And then the result of this multiplication will be we will create this operation add, which we'll call total. So this operation here will receive these tensors and has this name total. And this will just add the two tensors we created. So if we are using eager execution in TensorFlow, the default is to, when you run this script, TensorFlow will execute all these computations, and then in total you will have a tensor. It is just a scalar, it doesn't have a shape, and it has this value here. So you have this NumPy method on your tensors that can be used to obtain the values inside the tensor as a NumPy array. But note that tensors have a lot more code behind them, because they need to know how to do all of these things in the computation graph and keep the names and things like So then we can use this, we can chain other operations. For example, create a new C here, multiply, and then you have here the different steps on this computation graph where we are adding A plus B and then taking this tensor and multiplying it with C and obtaining the result there. So this is an example of what TensorFlow is doing when we do all of these operations. It's creating also this graph for execution. With eager execution, it creates a graph and executes it as we give the instructions. If not, we can create the graph first and tell it to execute later. But the important part here is that we understand what TensorFlow is doing in the backstage, so to speak, when we define all of these operations. So these tensor objects are fairly complex objects that keep track of all these connections, and that then we can use to train our network by computing the derivatives. If you want just the value that is stored in a tensor, you can use the NumPy method, and it will return the values there as a NumPy object. If the tensor is just a scalar tensor, as it is in this case, it will return just a number. If it is an n-dimensional array, it will return a NumPy n-dimensional array with the values. Okay, so let's implement logistic regression in TensorFlow using stochastic gradient descent to obtain our parameters. The idea of logistic regression is that we have a function that has some parameters that we can adjust, which we want to use to approximate the probability of a given point belonging to class 1. In order to do this, we're going to use this logistic function, or the sigmoid curve, which varies from 0 to 1 and can be interpreted as a probability. And so this will be the function that we want to optimize, would be this one, and it will be a function of the input that we receive and these parameters, the weights that we multiply by the features of each example, and this additional bias that we can use to shift the value where the sigmoid is responding. So we do this by minimizing the logistic loss. This is comes from using maximum likelihood for training the logistic regression. And so this is the loss function that we have here. So minus the average of this product of the target label that we want to predict. This would be 1 for class 1 and 0 for class 0, multiplied by the logarithm of the output of our function, plus 1 minus the label multiplied by 1 minus the logarithm. So how can we implement this? We will create this computational graph, which has this part here for computing the weighted sum of our parameters and the examples. We have the weights here. These are created initially with a random normal distribution, and these will be multiplied using matrix multiplication by the x value for the input. And then we add the bias here, and we pass this to the sigmoid function, which is a function that TensorFlow includes. So we will have the output of the sigmoid function there. And this is basically how TensorFlow will interpret our operations and create the computation graph, with also this information here on the gradients. So when we need to do gradient descent to optimize the parameters, TensorFlow knows how to compute all of those gradients because it's keeping all of the expressions for the gradients in the right place. Then we need to minimize the logistic loss. Again, this expression will end up being this computational graph where we have the logarithms, the products, the sums, and so on, and it will create the graph for this and include again all the necessary information for computing the gradients. So the idea here is that when we implement this, TensorFlow will create all of these graphs from the operations that we are combining together, and also include all the corresponding derivatives so that it can then compute the gradients when we want to do the optimization. So let's start by loading the data. We can load, for example, this gene data that we used before, and we will put the last column of our matrix that we loaded. So this one here has the y vector, which has the labels. And we will store the features, the first two columns, in this X, and then we'll standardize. So we'll compute the mean for each column. We will subtract that from the values, and we also compute the standard deviation for each column, and we divide by that vector. So we are using broadcasting in NumPy to do this standardization. If you don't remember how broadcasting works in NumPy, just give a quick review on the documentation, because this is very useful when you are manipulating data. But one important thing to remember here is that we have a matrix of 2 columns and n rows for our data, and we have a vector, a one-dimensional array for the labels. It's important to remember this because then things must fit together when we are computing the appropriate tensors. So let's create a function that gives us the prediction of our model. This is basically this expression here for the g function that depends on the parameters and the data. So we're going to create our parameters here as global variables. The weights will be a TensorFlow variable that starts with this shape and is initialized by the random normal. So this shape is 2 rows and 1 column, so that we can easily compute this expression here, multiplying the weights by the inputs, using just a single matrix multiplication. So to recall from last lecture, we have this matrix multiplication here. If we have the weights in 1 column and we have the examples in rows, then we can compute the product of each feature by the corresponding weight and add everything together for each example, and do this with just one single matrix multiplication. So this is what we can do here. We're going to use the matrix multiplication function of TensorFlow to multiply the tensor with a batch of examples by the tensor of our weights. In order for this to work, since our examples have 2 features, the tensor of weights must have 2 rows. It must be a column of 2 rows, because this tensor of example has 2 columns per row. And now what we obtain here is the weighted sum, or the added products of all the weights and the corresponding features using matrix multiplication, to which we're going to add the bias value. And the bias value is simply a scalar that we can start at 0, but then we will train it, we will adjust it to optimize it. So this gives us this expression here, this operation. So now we need to feed this into the sigmoid activation function to get the complete expression, and we can do that here. We apply the sigmoid function to this net result that we obtained here. Now there is one important detail here, because if we do this matrix multiplication, we obtain a matrix, a 2-dimensional matrix with as many rows as the examples we fed into the model, and as many columns as the number of neurons we have. So in this case it's only 1, it will be 1 column, but it's still a 2-dimensional matrix. And in our data set, we stored the labels as a 1-dimensional array, just the last column here, but as a 1-dimensional array. So in order for these things to match in the loss function, we can use the reshape function in TensorFlow and bring all of this into one single dimension. And this -1 indicates that we want as many elements as necessary to put this in a single dimension. This doesn't change much the shape because it was already one column, but it prevents it from being a two-dimensional matrix, and it's now a one-dimensional array with all the outputs of our sigmoid function, of our neuron, for all the examples we put in here. Since we can expect that we want to call the prediction function using, for example, a NumPy array with our examples, and since we need to have tensors to do these operations, we start by creating an auxiliary tensor here, where we use the NumPy array that is given to the function and create a tensor, which can be just a constant, copying that data into a tensor. So this will be the function to create the prediction of our neuron, of our model. And now we need to compute the loss when we compare the prediction to the desired labels. So this is the loss function here, the logistic loss. And what we're going to do is we're going to assume that the predicted labels are already a tensor, because they will be obtained from this prediction function, and this one returns a tensor. But the target labels, the y values, are probably a NumPy array. So we're going to create a tensor from that NumPy array. And now we're going to compute the cost function, which is the average, minus the average, or the mean here, this expression here, of these products, the target labels multiplied by the logarithm, and 1 minus that target labels multiplied by the logarithm of 1 minus the output. So we have this expression here, the tensor with the target labels multiplied by the logarithm of the predictions, and then 1 minus this tensor multiplied by the logarithm of 1 minus the predictions. Note that since we are using tensors here and these operations from TensorFlow, all of these operations in the computational graph are being associated with the corresponding derivatives. So we don't need to worry about that part. TensorFlow is doing that automatically. And all we need here is to return the cost. So we wrote the functions to compute the predictions of our model. We wrote the function to compute the logistic loss, the loss function that we want to minimize. And now we need to train our model. So in order to train our model, we're going to use automatic differentiation to compute or to estimate the gradient given a batch of examples. And to do that, we use these gradient tape objects from TensorFlow. When we create a context for a gradient tape object, for example, this tape object here from the gradient tape class, inside this context, TensorFlow will track all of the operations and the corresponding derivatives, so that it can then do the reverse pass, backwards pass, and compute the derivatives with respect to any variable that we choose. And this is what we can do here. We can obtain the gradient of this final tensor, which is the value of the loss function, with respect to the variables that we want. And we give a list of tensors which are the variables here, with respect to which we want the gradients computed. So in this case, these are the parameters of our model, the weight tensor and the bias tensor, and we want to compute the derivative of the loss function with respect to those variables. So what we do is, inside the context of the gradient tape, we do the complete computation. We start by computing the prediction for the batch of examples we have. Then we compute the value of the loss function by comparing that prediction to the target labels. And now this is the final tensor, which gives us the values of the loss function for all this batch. And we ask for the gradient of this value of the loss function with respect to the variables that we want to update. So now with this gradient function, we return the gradients, and I also return the variables themselves, which is strictly not necessary because these are global variables and we have access to them even outside the function. But it's useful so that I don't make a mistake on the order of these variables, because then when I'm going to apply the gradients, I need to give the right gradient to the right variable, and if I change the order, things will go wrong. So this is now how we can do the loop for training. So for each epoch in the number of epochs that we want, for example 20 in this case, we're going to shuffle all the data and then run through the batches that we want. So the number of batches per epoch will be the number of points we have in our data set divided by the batch size. In this case, I'm using a batch size of 1. This means that I'm presenting one example at a time, but we can change this and you can experiment with different values. So what we're going to do is for each batch, we're going to pick this number of examples given by batch size in the features matrix and in the corresponding labels. Since we are using these shuffled indexes, for each epoch, we'll be presenting the examples in different orders so that we preserve this randomness in stochastic gradient descent. And now for each epoch, what we're going to do is to apply this grad function that will do the whole computation. It will do the forward pass by computing the prediction for this batch of examples and the loss function, and then compute with the backwards pass the gradients that we ask with respect to the parameters to optimize. So this function will return two lists. It will return the list of the gradients given by the gradient tape and a list of the corresponding variables, which must be in the same order, otherwise this will not work. And now we obtain these two lists, the gradients and the variables, and we are going to use the optimizer to adjust the parameters. Now the optimizer in this case is an object of this class, stochastic gradient descent, where we can specify things like the learning rate, momentum, things like that. So what this object does is use the gradients to update the variables, and in this case it's simply by multiplying the gradient by the learning rate and then changing the different variables. So we need to give to this applied gradients method a list with the tuples of the gradient and the corresponding variable. This is easy to do with zip. This is a basic Python function that can take a number of arrays as arguments and return an array, a single array with tuples, where it puts the first element of this one with the first element of this one, and then the second with the second, and the third with the third, and so on. So we can, as long as we have the gradients in the same order as the variables, we can easily pack these together and send to the optimizer. And now the optimizer will change these variables as a function of the gradients for the variables. So this will be the training loop. For each batch, we will apply the gradient. So we will pass these examples through the neuron, compute the loss, and then compute the derivatives with respect to all the different variables and apply the update to the variables. Then when we finish one epoch, we run through all the examples, we can just compute the prediction for the whole data set, the loss for this prediction. So basically we are measuring the training error here using the whole training set, and then we can print out the loss value for this epoch. And this way we can look at how the training is going and see if things are converging nicely and so on. So this will be the first thing you're going to implement, just to simulate or to implement logistic regression in TensorFlow using this stochastic gradient descent for training. So this is what we have with this data. This data file has linearly separable classes, and you'll see the error function going down. You will not see these plots, of course. These are something extra, but you'll see this print with the values. The values should be going down gradually as we reach we fine-tune the parameters there. So we can use this to solve the OR problem. We can create an artificial set of data points. So this we can consider 0 to be false and 1 to be true. 0 or 0 will be 0, so false or false is false. And then an OR with a true value will always be true, so the others will be true. And we can just use this as our data. We again create the variables for this. We have the prediction and the loss. In the loss function, in this case, I'm using the mean squared error. So I'm computing the mean of the square of the difference between the target and the prediction. You can also use the logistic loss if you want, but in this case, I'm using the mean square error just to show you that we can change the loss function. As long as we are using these operations with tensors that TensorFlow supports, then all the issues about the derivatives are automatically taken care of. So the actual expressions for the derivatives here will be different from the previous example, but this is done automatically by TensorFlow, and we just use the same approach. We use the gradient tape to track this computation and the derivatives, and then we update for each epoch using the optimizer. So the code is basically the same. The big difference here is that we have only 4 examples. So you're going to need more epochs in order to train this, because in each epoch you're only going to go through 4 examples in your training. Okay, so the OR problem can be solved like this. This part is the same as we saw before. We do the loop, we loop through all the epochs, we shuffle the examples, take the mini batches, compute the gradients for the variables, and apply these gradients using the optimizer that will update our weights. And so the OR function also works. It's linearly separable, and we can distinguish the true values here in red from the false value in blue. If we change the labels for the exclusive OR, so the difference between OR and exclusive OR is that in exclusive OR, if we have true, exclusive OR true, the result is false. So this is the only thing that changes. We change this 1 for the OR to a 0 for the exclusive OR. And now this no longer works with 1 neuron. We cannot get the error to go below 0.25. Remember, this is the quadratic error. So 0.25 is the square of 0.5, and we are basically getting half of the points wrong. Because this is no longer linearly separable, we cannot do this with just 1 single neuron. So here comes the part where we're going to do the exercise. You can experiment 1 neuron with this kind of data. For example, this gene data file is linearly separable, but if you try it with the exclusive OR or with this data set here, you will not get very good results, because 1 neuron is just a linear classifier and you cannot classify these data properly. So what you need to do is to implement the multilayer perceptron. For example, let's just add 1 hidden layer in this way, and this hidden layer will change the representation of the input. So this is the same data set looked at from the perspective of the output neuron, but now it's looking at the output of the 2 hidden layer neurons. And since one of them puts this this input value here on a high output and the other 3 on a low output, so let's say this neuron is represented on this axis, and the other does the same thing on this axis but for a different input, one high and the other low, this neuron can now easily separate the data with a linear classification, which is all it can do, but the data now has been transformed by the hidden layer. So this is what we're going to do. You're going to generate this artificial data for the exclusive OR problem, and now you're going to create 1 hidden layer with 2 neurons. So remember, the trick here is that if you have your examples in rows in one matrix and the features are columns, and you encode your layer of neurons where each neuron is a column and each row is a weight for the neuron, you can do the matrix multiplication like this, and you get the outputs from all the neurons in different columns for all your examples in different rows. So if you remember this matrix multiplication, you can easily create any layer using the appropriate tensor by putting your neurons in columns and then doing this multiplication. So now you're going to have to change the prediction function, and remember to also indicate all the variables you need in the when you call the gradient tape. But you will have this result now because the hidden layer will change the representation of your data, and you'll be able to, using the final neuron, separate the two appropriately. Note, however, the number of epochs I'm putting here. So there are lots of epochs to guarantee that the network can learn, because now not only we have more parameters, but since we have more layers, the layers in front usually have to wait for the layers in the back to learn, and the layers in the back need to get the input from the errors propagating through the layers in front. So training multi-layer networks takes a lot more examples until everything fits together nicely. So you can see it here on the loss function. We have we are descending here, but then there is some we reach some point where things are better organized, and then the loss reduces very fast as the last neuron now learns to classify things properly. So you'll have to also change the number of epochs and experiment a bit with this, but this will be the exercise, implementing this network and applying to those different data sets. Okay, so what we saw here was these basic elements of TensorFlow: the constants, the variables, the functions that you can use for the activation, the loss, and so on, and this basic scheme where we create the forward pass. So the prediction is a forward pass through our model where we compute all the activations and the output. Then we also include there the loss function, which compares the output of our model with the desired labels. And then we use the gradient tape to keep track of all of the operations in the forward pass and do the backwards pass where the derivatives are chained together. So this is done automatically by TensorFlow because TensorFlow knows all of these derivatives, and we get the gradient information with respect to whatever variables we want to update. And then once we have that information, we use the optimizer object to apply the updates. The reason for this is that the optimizer object can be more sophisticated. It can have things like momentum, it can rescale the different updates and so on. We're going to see more sophisticated optimizers further on in the course. So we use the optimizer to take care of updating our parameters. And this is the basic scheme that you're going to follow, starting from these simple examples with one neuron and then implementing the multi-layer perceptron. You can use the one I showed here, or even implement the one with two hidden layers that I showed in the previous lecture to use on the other data files. And then you can experiment with momentum, with learning rates, with the number of epochs and so on, just to get a feeling for how these things are working. So these are very simple networks. They will not be the architectures that we're going to focus on in the course, but this is just a starting point so that you get a feeling of how these things behave when you're training and how they respond to these different parameters that you can adjust. Okay, so that's the lecture for now. I'm going to log into Zoom and join you in the Zoom session if you have questions, and then we'll start the tutorial at 11.